Hi, my name is Satoshi Hoshino from Utsunomiya University, Japan. In this video, I'd like to introduce our work titled Driving Assistance by Personal Mobility Vehicle based on shared controller with semantic load segmentation. This research was presented at the International Conference on Control, Automation, and Systems 2025. Public transportation often does not cover the first and last parts of journey. For example, from the home to the nearest bus stop or from the station to the final destination. That's why we focus on personal mobility vehicles, PMVs, as a new means of first and last mile transportation. However, as you can see in this video, sidewalks have many obstacles, so driving a PMV safely remains a challenge for many users. The goal of our research is to enable the PMV to assist safe driving while incorporating the user's directional input from the joystick so that it can avoid collisions with obstacles. To achieve this, the PMV needs to compute control commands such as linear and angular velocities while considering the surrounding environment. We have so far proposed a shared controller based on an attractive repulsive force model. Sorry, the paper was written in Japanese. While a 3D LiDAR was previously used in this work, an RGB camera is used instead. This is because a problem caused by using the 3D LiDAR failed curve detection on roads due to decreased point clouds. It is usually possible to detect curves as you can see in this picture here and here. On the other hand, since 3D LiDARs have minimum measurable distance, it is sometimes difficult to detect curves on narrow roads here and roads with many obstacles, as you can see here. As a result of failed curve detections, the risk of collisions is increased. So we use an RGB camera and propose a novel shared controller. The PMV employs semantic segmentation to identify drivable road surfaces that are free of obstacles between curves within the captured images. These segmentation images are used as input to the shared controller along with user's joystick input. Let me give you an overview of the proposed shared control system. This shared controller processes inputs from both the user and the PMV and computes control commands as outputs. The user seated on the PMV here can steer it in the desired direction by tilting the joystick. In other words, the user's intended driving direction D can be determined by the joystick's tilt. Meanwhile, the PMV equipped with a camera captures RGB images of the surrounding environment. By applying semantic segmentation, the PMV classifies all pixels as either drivable road surface or non-drivable areas. The shared controller is based on an attractive repulsive force model. The attractive forces are derived from the user's driving direction D via the joystick, while the repulsive forces are derived from the road segmentation images I. The resultant force acts on the PMV to determine the control commands U as outputs. For semantic load segmentation in RGB images, UNet is used. The UNet was trained from scratch on a dataset of 850 images, and the maximum IOU for 200 validation data was about 90%. This picture shows an RGB image. We can see curves on both sides of the road, as well as a traffic cone placed on the road as an obstacle. And this picture shows the road segmentation images in which pixels corresponding to the background, traffic cone, and curves are all shown in black. In other words, only the drivable road surface for PMV is shown in red. Therefore, by using images as inputs to the shared controller together with the user's driving directions, the PMV can accurately identify the drivable road surface and provide driving assistance. Driving assistance is provided by the PMV through the shared controller based on an attractive repulsive force model. Particularly for collision avoidance or driving assistance, repulsive forces are derived from the semantic road segmentation images. To compute the repulsive forces, we focus on the centroid of the road pixels as shown in this figure. Assuming that now the robot is on a road of infinite width with no obstacles, the centroid is located at this point. This coordinate point is defined as the reference centroid C. The centroid of the road pixels in a segmentation image at time t is denoted as CT. So the spatial relationship between C and CT varies depending on the road width and the presence of obstacles. In this environment here, an obstacle is placed on a road of finite width. In this case, CT is shifted from C toward the bottom right as illustrated in this figure. As a result, repulsive forces are derived based on the displacement of CT from C as you can see here. So let me first explain the repulsive force based on the displacement of CT from C. The repulsive force Fr is expressed as you can see here. Kr represent a constant. Rho is the Euclidean distance, Euclidean pixel distance between C and CT, and rho 0 denotes the threshold of rho for applying Fr to the PMB. These repulsive forces enable the PMB to avoid obstacles and curves. In contrast, attractive forces determined by the user's driving direction D move the PMB toward the destination. The attractive force Fa is expressed as you can see, where Ka represent a constant and Xd and Yd denote the X and Y components of the joystick tilt. From these repulsive and attractive forces, the resultant force F acting on the PMB is given. Finally, as shown in the right figure, the control command is determined based on F, allowing the PMB to navigate in the direction of the resultant force F. Okay, in this experiment, the proposed shared controller is applied to a PMB for driving assistance. This is a PMV used in this trial. An RGB camera is mounted on the front side at the height of 0.2 meters. So the PMV can capture RGB images at the frame rate of 30. The horizontal field of view is 69 degrees, and the size of segmentation images is 320 times 240 pixels. For comparison, a 3D LiDAR was mounted at the height of 0.6 meters. The maximum velocity is 1.0. For collision avoidance, the angular velocity is determined within plus minus 0.35. This picture shows the road environment. On the road of a width of 3.5 meters, two traffic cones are placed at each of three locations as obstacles. Additionally, curves are present on both sides of road. In this environment, the PMV navigates from the start point S to the goal, covering approximately 14 meters. For this experiment, the users continuously tilted the joystick forward, regardless of the PMV's direction. In all trials, the PMV successfully reached the goal G with driving assistance based on the shared controller. First, these figures show the navigation trajectories. In each trial, the time taken for the PMV to move from S to G was approximately 27 seconds. From this point on, we focus on the results of the first trial for further discussion. Let me first show the transition of the centroid of road pixels CT. Compared to the reference centroid C, CT was shifted downward and repulsive forces continued to act on the PMB. As a result of driving assistance, even when the PMV navigated straight ahead, its speed did not reach the maximum of 1.0, as you can see here. And moreover, it can be seen that the PMV successfully avoid the obstacles at 3 locations while further reducing its speed. These videos show the navigating PMV in addition to the segmentation images. In the segmentation images, 3 vectors indicating the directional input D from the user, the displacement of centroid of the drivable load surface CT minus C, and the resultant force are displayed. The proposed shared controller was applied to the PMV for driving assistance in different load environments. First, we place the 6 traffic cones in a row of the same road as in the previous experiment, completely blocking the path. In this environment, the PMV eventually stopped just before the obstacles. In the next environment, although 6 traffic cones were placed in a row, the 5-meter wide road still had drivable area on the left side here. As a result, the PMV successfully navigated toward its destination while avoiding collisions with both obstacles and curves. The PMV was also able to pass through a narrow branch-like path while reducing its speed. Even on an actual sidewalk, the PMV successfully provided driving assistance that ensured safe navigation without collisions with a tree or the wall here and here. Okay. In conclusion, we propose a simple yet effective shared controller based on an attractive reversive force model to assist safe driving by the PMV. In order to integrate user input with the PMV's autonomy, the attractive force and repulsive force were generated based on the user's driving direction and load segmentation images. The resultant force computed from these components determined the control commands, the velocity and angular velocity applied to the PMV. The experimental results demonstrated the PMV successfully avoided collisions while following the user's intended direction. So these results validate the effectiveness of driving assistance by the PMV based on the shared controller. Finally, let me show a video of an experiment conducted on an actual sidewalk with a pedestrian. Okay, that concludes my presentation. Thank you very much for your kind attention.